you do this on your own. So here's how we solve the Bellwork for today. Okay? This looks kind of like the Bellwork from yesterday. We're kind of talking about the same thing, similar to the lab. Well, now this time, instead of giving you distance it went when we're done pushing it and the time, now we're going to give you the full scenario where I push the chair and I sped it up. And then I stop pushing, I let go, and I let the chair just slide and glide to a finish. So how can we solve this problem? So I drew a picture. You guys know I'm not very good at art, but I drew a picture anyway. The picture, what is the brakes on? The picture looks something like this. Since you're not going to be the cameraman, Boyd, I guess I'll have to do it. So I drew this picture to kind of define what I'm doing, right? So you have two parts of this. One part, you're speeding up, you're pushing the chair over 4 meters, and it lists the acceleration number on the board. And then you let go of the chair, and then it just glides to a stop at some point. Okay, and as per the assignment, we're doing this as if we were doing this in the commons. So your acceleration on this part is going to be different than what we had in the hallway. And you're going to base that on the Bellwork from yesterday, what you got for an average acceleration from the Bellwork yesterday, and we'll go through where that fits in. So the trick with this is you have two different kind of independent parts of this question. So as such, I have two different sets of variables to consider in this problem. So for the first part, what do we know? Jump in anytime. What do I know for the first part?
The distance you accelerated over.
The distance, what is the distance?
4 meters.
Okay, what else?
The acceleration.
What is it?
2.18 meters per second squared.
And what else do I know? Y initial velocity. Started at 0, I started at rest. Now there's a couple different ways to go from here. One way is you can kind of solve out using your equations. You can just solve everything out on part 1. You can figure out final velocity, average velocity, time. You can figure all that stuff out. You can just solve it completely out. Use your formulas and figure out all the info. Some of you did this. But there's another way that maybe is more efficient, maybe slightly less work, where I'm going to consider part 2. Before I start doing any of the math, I'm going to think about what happens in part 2. Right? And so now part 2 is we let go of the chair and it just glides to a stop on its own, right? It has some velocity and we let it just go through the commons until it comes to a stop. So let's fill out what we know. What of these things then are we given in this problem?
Final velocity.
Final velocity is what?
0.
0, right? Because we're just going to time it until it gets all the way to the end. What else do we know? Acceleration. What do we know about the acceleration? It's half of whatever we had yesterday. Whatever the acceleration was in the hallway, I'm going to propose that on tile floor, it's going to slow down slower, if that makes sense. Right? The tile is going to be much smoother. You're going to have less friction, whatever. So I calculated this as 0.2315. Negative 0.2315 meters per second squared. Now it's just based on what we did yesterday. Now, some of you didn't get all 3 of the trials from yesterday and you didn't average them together. You just used the acceleration you figured out for one of them, which is fine. You're going to be close enough. But I averaged all of them and I got this number. So now, what are we trying to find? What is the question asking us for? Distance and time when, though? For part 2. We are trying to solve for distance and we're trying to solve for time. Now you can go shopping for an equation here, right? We have our 5 equations. Which of them will use final velocity and acceleration and get us distance and time? Or do we have one? I'll save you the search. No, none of those equations will get you there with this much information. Right? We need something else. But fortunately, these two situations are connected, right? They're related in some way. At this point, at the let go point, right? Two of these variables are closely related from both of these lists. What will they be? I'm glad your sandwich was there. We're all glad. Which of these are related? Some of you figured this out. What number on the left is going to be the same as on the right? What's that? So this number here will be the same as the initial velocity for the other. Do you understand why that is? Right? You're pushing the chair, you let go, right? So the final velocity of the first part becomes the initial velocity for the second part. So now let's go backwards. Can we solve for final velocity in the first part? Can we just get that? Do we have an equation that will get us there? Seth? Which one? Which equation gives us final velocity when we know acceleration, distance, and initial velocity? The fifth equation, right? VF squared equals 2AD plus VI squared. This is pretty easy to solve, right? What term here goes away? What can we immediately get rid of here? Yeah, VI squared, it's 0. So now we just solved this. And again, many of you got this. So VF squared equals 2 times our A number, 2.18, times distance, 4.00, and you get VF squared equals, what was this number? What was the number? Somebody, anybody, they got this. Seth, I know you had it. 17.44. And then how do we get rid of the square? Square root it. VF equals, what was it, 4.18? Meters per second. So I can put this in here. And now, what can I do with this number? Do I need to solve for time and average velocity for part 1? No. Do I need that information? Will it hurt me to get that information? No, but we don't really need it. You can solve for it to be sure. You can figure out how long you push the chair to speed it up. That number is out there, but we just really don't care about that because the question didn't ask us that. Right? And now we can go shopping again. We're trying to find distance or time. We're going to need them both. Right? Now, how can I solve for either of those variables for part 2? Which equation can I use? Equation number 3. A equals VF minus VI over time. So I'm going to rewrite this as time equals VF minus VI over A. Plug all that up, and I get time equals what? 18.1 seconds. This pen is running out. Where have all the pens gone? So now I have a time number. Now what can I do next? So let's plug time into our list. 18.1 seconds. Now how do I solve for distance? Which formula can I use? Okay. True, but I need what to do that? Okay. So what's my average velocity? How do I find that?
Initial plus final over 2.
Okay. So what's that going to be? 2.09 meters per second. And then you're saying we can then plug that into the average velocity formula?
Yeah.
V av equals d over t equals distance equals time times v av. Time was 18.1 times average velocity 2.09. Do that math, you end up with 37.7. Anybody spot a different equation they wanted to use to get this answer? Yeah, you could have used distance equals 1/2 AT squared plus VIT. Right? And then you wouldn't have to have average velocity figured out? Yep. So let's play make-believe that we use that one. Let's see if we get the same answer. Honestly. Cam, it's for you. Cam, the phone, it's for you. Bro. Bro, just, hi, climber's room. Bro. You guys are selling back in table 6. All right, so let's figure this out. D equals 1/2 times 2315 times 18.1 squared plus 4.18 times 18.1. Anybody want to do that math? Ty, you're the one that volunteered. Do the math. 0.5 times 0.2 times 18.1 plus. Dude, that can't be right. 1/2 AT squared. Dude, I got a huge number.
Yeah, I got like
113?
mine's like 2 million. Is that second number 2,315?
Yeah, but that shouldn't be right. VI plus VF.
Climber, your decimals.
Why does that not work? I know, my decimals are terrible.
It says I don't even see it. 315 negative. How did you do that?
Oh, I didn't do that. Boyd.
It's rookie.
God, Boyd, you're winning.
Climber was selling. Yeah, like on 2,315 on that circle. Because you should know the numbers.
All right, so that works then. If I make this negative, because I didn't at first, then that works. You still get 37.9. Bruh. Good old minuses and pluses. All right, so again, how this works. Part of this is kind of like a T-chart. Part of this is kind of like trying to figure out how we get from one thing to another. Somebody earlier in the day asked me, why can't we have a worksheet with a bunch of these on it? Right? So, well, you would never do it, which is part of the problem. So why would I expend all that effort to make 10 of these questions? Secondly, like these questions take 10, 15, 20 minutes to answer. So if I handed you a worksheet with 20 of these, you'd be doing this till February, and then we wouldn't get anywhere. Okay? And also, let's make it optional. Oh, Boyd.
I would do it.
Of course you would.
If it was optional, I'd do it. If it was mandatory, I wouldn't.
So guess what? If you read the chapter and actually do the questions that are in there, there are several more problems just like this. If you did the APP, you would have answered a question like this about, a plane landing on an aircraft carrier. There's a question just like this. The next one was a motorcycle taking off or some other kind of thing. So there are more questions like this. This Bellwork has been posted online, the Bellwork from today and yesterday. So if you still weren't sure exactly how to solve that, the raw materials are there. Also, I'm available before school. I'm available after school. I'm available during study hall. If you need some clarity or you want to kind of work through more of this, stop by. I can help you figure it out. None of the math in here is hard. About the most complicated math we just did was figuring out a square root of something. You guys have been doing that since 8th grade. The math is not difficult. What is difficult is reading this question, figuring out what the scenario is, and what kind of things I need to figure this out. And some of that is practice. Some of that is actually doing the work. Some of that is carefully reading through what it's asking you. Guys, there's a ton of math in physics, but none of it is going to be a giant worksheet where you just multiply two-digit numbers together over and over and over. We're just not ever going to do that. Right? It's going to be giant word problems like this, where you have a scenario that you have to kind of imagine. The beauty of this Bellwork is you don't have to imagine this. We literally did this last week. We pushed chairs in the hallway. Y'all did it. You measured your results. You have some data in there. So we've done this. You don't have to imagine this and play make-believe. We literally did it. You just got to remember. And then how you plug in the numbers, again, this is an algorithm. This is a way to do this that works. Just plug the stuff in. Go shopping for an equation that will help you solve for all the stuff. Again, you didn't need these two things to do this problem. But it wouldn't have hurt you if you figured them out. It's just plugging in more of the stuff into the equations that we already have. This is what physics is. It's figuring out problems like this with some kind of real world thing. Real world, we pushed chairs in the hallway. We actually did this. Right? That's what this stuff is.